Hello, I'm going to be starting my machine learning series where I'll be covering different concepts from linear regression to the encoder and decoder. So for this first episode, I'll be covering how to do linear regression and how to do cost functions, regularization, and feature scaling. And I want to also address overfitting in this episode. Uh, what my main point of the series is to cover things like later on how to do transfer learning with ResNet, for example, or how to do it in TensorFlow, and not just understanding it conceptually, but also understanding how to do it on Google Colab, for example, and how to, like, for example, import Kaggle data. Found annoying early on. So I'll be starting with the types of machine learning. So machine learning is a way to use data to perform tasks without being explicitly programmed to do the task. For example, like spam detection, the classic machine learning example, or search engines in some cases use data. So could you think of a way to easily detect if something's a spam or not? You can't really explicitly program that pretty easily. But if you give data to an algorithm, for example, it's able to independently find a solution to detect if a email is spam or not. So the types of machine learning are supervised, unsupervised, self-supervised, and the distinction is if the data is labeled. So supervised learning is like giving images of birds and saying if the bird is a bird or not. So like labeling images. So like you have like a huge data set and the data could be labeled like different categories. Like for example, like maybe different types of trees. Like each tree is like one tree is labeled as redwood, for example, and the model is able to learn off that and, for example, do detect later on if it's a certain label or not. Unsupervised is a little different. It's more for grouping. An example is of unsupervised learning is anomaly detection. It's able to detect if a new photo is different from all the previous photos, for example. Like it's different, it's an anomaly. It also works with. It could also work with k-means. It could also categorize the data so that you're able to label the data. So this goes to self-supervised learning. It's the concept of getting an unlabeled data set, just photos, for example, and using unsupervised learning, which like to categorize it, use then to label it. Then you run supervised learning with the created labeled data set. So the distinction, in my opinion, for supervised and unsupervised is if the data is labeled. Is the data like are photos having the title like bird? It's like a test where you have the answer key versus a test where you don't have the answer key. The test where you have the answer key is the supervised learning. The test without the answer key is the unsupervised learning. So it doesn't have to be just all labeled data or all unlabeled data. It could be semi-supervised. This is a data set that's partially labeled, and it's kind of in between the two. So the other types of machine learning are reinforcement learning, which is you create an initial policy or rules to follow, and then based on the rewards and penalties that the in this case, I guess, machine learning model takes. Like, for example, you give it the instructions to jump off a cliff, for example, and the goal of the AI is to, like, robot, for example, is to not get damaged. So, jumping off the cliff causes the robot to get damaged. So, in this case, it gets a penalty. So, in the next time, it'll update the policy so that it no longer jumps off the cliff, even though originally the original policy was to jump off the cliff. It updated it because it gave it a penalty because it got damage from it. Another way to see it is, for example, you could have rewards. So, for example, you could have it do random actions and it just moves different keys all over the place. But then it discovers if it holds the W key, it leads it leads it to go farther in the video game, like it goes farther along the track, so it gets more rewards. So the next time it happens, the policy updates so that it holds W the entire time this time. So there's different types of learning types. There's online versus batch. Online, you could think of it like it learns continuously. It could get a continuous stream of data. So like, for example, like it's able to look at all your posts and continuously use the new post to train itself. Batch is like you train it in one go. Like you train it on all the Wikipedia data today, but you can't. You when you want to update it, you have to retrain the entire thing from scratch. Online, you could kind of have a trained model and kind of update it, so it's able to continuously learn. While batch is like, oh, I have to make a new major release every time I have anything I want to change. The other types of learning are instance and model-based learning. So instance-based learning, you can see on the right the picture of the circles and the triangle. So it uses the data that's the most similar to it to predict what the result will be. So from the right example, for example, you can see how there's 3 circles. So, and 1 X. Since there's 3 circles around it, it's probably going to be a circle. So it's going to predict circle. But in model-based learning, on the left, you can see how it's a line. So it just uses boundaries to be able to determine if it's X or a circle. So those are the different types of learning, and I'll be now continuing finally to linear regression. So linear regression is the process of determining a linear relationship from a graph of data. This could be an example, could be finding the line of best fit in a set of data. This could be used to predict house prices from the square feet of the house, with the square feet of the house being the Y and the price of the house being the mx plus b. So let me just draw that right now. Y equals mx plus b. This is a simple example of linear regression. But this could be seen as the weights, and this could be seen as the biases, and this could be seen as the input. Weight, bias, input. But we don't just need one input. We could have multiple. We could have something like this: m1 x1 plus m2 x2. We could also have multiple biases. We could also plug in previous biases, linear regression into results into the next days, and do all the weights again, same exact weights again. And this is called recurrent neural networks, which we'll learn about later. These weights and biases could be done in the form of matrices, for example, and these could be done, M and X could be a dot product between the two. Dot product. Why is it being a matrix useful? It being a matrix is useful because the matrix could be used to hold all the pixel RGB values from all the pixels, for example. Or it could be used to hold a lot of parameters in the embedding space in, for example, words. So let's go over the loss function. The loss function in this case is the predicted result from linear regression, which is y hat minus the real result, and then squaring all the differences and dividing it, finding the average of it. When you're finding mean squared error, you want to lower this result the most. This process is called gradient descent, where you use the derivative of this, the mean squared error, and set the derivative so that it goes straight to 0, approaches 0. So you start from this case over here, then you go here, here, here. So this is called gradient descent. And this has a learning rate, which is the amount you move at every step. There are other versions of gradient descent like atoms, where the learning rate increases as it steps more. So it's able to adjust its step rate, so that's able to approach the minimum loss faster. Back propagation can be seen as a way to get the gradients through partial derivatives. Like, for example, you have y equals mx plus b. How do you lower the cost function from here? Well, you find the partial derivative of x by dz. For example, z being the mean squared error. So the dz by dx. So you're going to see how to change this to lower z. And that'll be it for linear regression and loss functions. And there's additional things about linear regression that you should also be aware of, where the problem of overfitting, where the data is able to fit the data precisely, but when new data comes up, it misses entirely. This is called overfitting because it works only on the training set but does not work on the test set. So it works when you in the test environment but does not work outside of it. So how do we fix overfitting? Well, we could do something called add a regularization parameter. Which will be something that will be added to the gradient descent process to prevent it from reaching the bottom and overfitting. Or you could remove variables, because maybe adding all the house price, home color, and everything caused it overfit. So maybe like remove a few variables, or remove variables and do dimension reduction, which is a form of unsupervised learning to remove variables. Thank you. So there's two functions I want to cover before the end of this video. It's the Sigmoid and Relu functions, which will be later used in the tutorial about how neural nets work and how to use them. So Sigmoid and Relu are the two functions that are used. Relu is essentially finding the max between 0 and the function and removing all the negative values, while Sigmoid, in this case, takes a function value and sets it between 0 and 1, with, for example, a higher value being closer to 1, while a lower value, negative value, could be closer to, for example, 0. So what do Sigmoid and Relu do? Well, they both solve different problems. Relu, there's a problem called exploding and vanishing gradient. Explode. He explodes upwards. Vanishes to 0. So you might be asking, how does this happen? So you originally start with one mx plus b and another m, and then when you put it through another function, let's say like this is like a simulation of going through multiple layers in a neural net. This happens every layer. It could become 2 to the 10. For example, let's say 2 was the original m value, but m happens multiple times. M happens times, for example. It becomes 2 to the 10. This is a super huge number, maybe 2 to the 64. How do we read this? We can't. That's called an exploding gradient. So how do we solve an exploding gradient? We set the value between 0 and 1, which is in this case a sigmoid. How do we solve the vanishing gradient, where it becomes m 1/2 to the 26, for example, or 64? We use Relu because we take the high value and we remove all the negative values, and we prevent the value from being super close to 0, essentially 0. Vanishing gradient. Thank you. This will be the end of the first video. The next video will be covering how to do use neural nets with TensorFlow, and how softmax work. Thank you.